this chapter ends up, when we're done with it, and you see it on the exam, the problems end up not being that difficult. But when you first see it, it seems a little weird because we're entering into the electron. What's the electron of subatomic particles doing? And things get a little strange. Here's a quote. Let me read this. The modern physicist is forced to admit with some embarrassment that although he or she can formulate powerful and a beautiful mathematical theory of atomic and molecular behavior, she or he cannot be sure exactly what the theory means. That's by William Cropper. And basically saying we have all these theories, but to understand them can be a little difficult. If you watched my TED Talk on God and science, I kind of get into this. There's these weird things that happen where for subatomic particles, distance can become irrelevant. Time can become irrelevant or a non-factor. Things occur with probability as opposed to certainty. So all these strange things start happening, and that can, kind of boggles our mind and even taxes our vocabulary on how to explain it. My TED Talk is basically about how that has an interesting connection to theistic worldview. So we're going to see how it goes. Let's see, chapter, what chapter is this? 7, I think. 7, yes. It's basically called Electrons and Atoms. It's about quantum theory. We're going to do a few terms before we get into the core of the chapter. So we're going to start with some terminology and such, and just to see our flow here. This is on page 55 of the reader. We're going to do some terms. Some of these terms will come up later in the chapter. And then the first section of the chapter we're really going to tackle is comparing two things: classical mechanics, which is, I'll say more about it, but it's kind of what people used to think and still holds with quantum mechanics or modern science. Okay, that'll be the first section of the chapter. All right, but first some terms. Electromagnetic radiation. Electromagnetic radiation is a form of energy. It's a non-ionizing form. That means typically it can't hurt you, but it could be ionizing. It basically has two fields, as we say. An electric field, thus electro, and a magnetic field, thus the magnetic term. And those occur perpendicularly. I think I have a picture of that right now. But basically, this is radiation propagated as waves, okay, through a medium or a vacuum or what have you. Now, there's two kinds of waves. There's, like, if you think of an ocean wave, that wave moves, so it's translated over a distance. But there's also waves that don't move. So, does anybody play a stringed instrument? Okay, that's weird. But sorry that you're not musical, but there are these things called stringed instruments. You can pluck the string, and the wave doesn't move; it just vibrates on the instrument. That's called a standing wave. And if you know anything about it, you can pluck the string, then tap your finger somewhere on it and make a harmonic or an overtone, which would give a different sound depending on where you touch your finger to cause what we would call in science a node. That would cause a different waveform on the string. So there's two types of waves. Let me show you a picture of a wave, just so we're on the same page as far as terms go. Okay, here's a wave. You need to know the term's amplitude, usually with symbolized by a capital A. You need to know the term node, which is where the wave crosses the x-axis. Okay? So where it crosses the x-axis, or where y equals 0, where the wave function equals 0, that's what we call a node. And there could be a number of nodes. We also have what's called a wavelength, symbolized lambda. That's where one cycle of the wave occurs. So to go down and up before it repeats again, that would be called a wavelength, literally a length. And we're talking about sine and cosine waves. So you will see in some of the math of this chapter sine and cosine functions. Okay? We're not going to really use them, but you will see them as we progress through the chapter. Okay? So be familiar with this terminology: nodes, amplitudes, and wavelength. Okay? All right. One more term that kind of goes with these wave terms is frequency. And that's symbolized by the Greek letter nu. It looks like a V that is falling over. Okay? So if you're in brats, like sigma nu or something, then you're set in this chapter when you see all the Greek letters, or whatever. So this represents the number of crests or troughs passing through per unit time. So for example, if this was moving fast per unit time in one direction, say to the right, that would be the frequency of it. Moving slow, very few, this is called a crest, the top, or a trough, the bottom, crest, trough. There's very few troughs per unit time, that's a low frequency. Okay? Frequency tends to be related to wavelength. For example, let me get a different color out here. If we see a wave like this moving very fast per unit time, this is a high frequency or high wavelength, a high wavelength situation. This would be a low wavelength situation. And mathematically, if we take wavelength and multiply it by frequency, wavelength is a distance or a length, and it's in meters or it could be in nanometers. Frequency is a frequency that's in hertz or 1/seconds. These are the SI units, by the way. Hertz or 1/seconds are the same thing. 1/second is called a hertz. It's a 1/time unit. And that's frequency. If you multiply those two things together, you can see you get interesting units. They're meters per second when you multiply it together. That's a velocity. And those two multiplied together have a certain velocity we call lowercase c. Lowercase c. And this is the speed of light. It's a constant in a vacuum. It's 2.9979 times 10 to the 8th meters per second. What does this mean? Wavelength and frequency are variables. So since c is constant, if you know wavelength, you can find frequency and vice versa, merely by plug and chug. Okay? So that's one of the formulas, our first formula for the chapter, really. And I have a little video on it. Just C equals LV. You want to see that? Okay. Now I'm going to turn the page a couple pages here. We're going to go to page 57 of the reader and page 247 of the textbook. All right. I don't know if you've ever been near a body of water, but sometimes, especially little kids, sometimes boys, like to, once they get to water, they like to look for rocks and throw rocks in the water. That's super fun to them. And if you throw the rocks in the right way, like two rocks land in different spots, you'll see the waves from the rocks start to overlap, and you form what we would call an interference pattern. Okay, so this would be an example of an interference pattern. This also occurs in chemistry. If we have two atoms together, they generate these waveforms, and they also can create an interference pattern. Okay? This is also an interference pattern. When the two waves that are coming from both sources overlap to make a bigger wave, they're additive. We call that constructive interference. When the two waves come together and are subtractive, and they make a null or a void spot, then that's called destructive interference. So there's two types of interference: constructive interference and destructive interference. Let me show you by this diagram right here. So again, just simply in 2 dimensions. If two waves, you see how these waves line up right on top of each other? Well, if they come together and hit right on top of each other, they're going to be additive, making a bigger wave with higher amplitude as a result. This first one's called constructive interference. Okay? Constructive interference. Now, imagine the opposite scenario. If you have two waves and they are not lining up, they're out of phase, we might say. They're out of phase with each other, so a trough and a crest line up. When they add together, they're null. There's nothing left as the result, and we call this destructive interference. Destructive interference. 2 types of interference. We describe this type of interference here in this chapter, but we're actually not really going to use this besides just knowing what it is until chapter 10. Okay, so you have to put this in a little bubble, and you'll see what we're going to do with this in chapter 10. I'll pop that bubble for you. Okay, don't worry, I'm popping bubbles. All right, couple more sets of terms here. There's different ways that we can alter light. And 2 ways we're going to teach you in this class. If you're a hippie, or you know hippies, they like these things called prisms. And they hang them in their windows and stuff. And if you have a light, and you passed it through a slit just to focus that light, and it goes through a prism, that prism can separate out light into colors of the rainbow. Okay? And so it's separating out what we call visible light, which is electromagnetic radiation, a type of it, into different colors of the rainbow. That's one way to separate out light. There's a second way to separate out light that you'll learn in this class, and that's called a diffraction grating. And I was going to bring one, but they're so old, I couldn't find one before class. But if you have something called a CD, separate from the textbook, this is 247, your grandma has heard of this, and you put it in the light. You see the color patterns there. That's happening because there's a grating, kind of unintentionally, on the back, made to play music, but it works as a diffraction grating, where the grooves in the CD on the back side are separating out the light. And so thus when you turn it in the light, you see the different colors of the rainbow. And so this is not separated by a prism, but by diffraction grating. So just a different way to separate out light and bend light around. All right. Now, we're about to start section 2. Okay? And we're going to start, the textbook and the reader starts this comparison of what's called quantum mechanics and classical mechanics. So let me introduce the idea right now, and then as we progress, you'll see this concept occurring. So this is going to be the main concept of the chapter. Classical mechanics, if you take, has anybody taken physics 7a or high school physics yet? Like distances, yes, good. Distance equals rate times time, acceleration, all that stuff. You remember that from physics? That's what we call classical mechanics. If you're taking physics 7a here or 9a, that's classical mechanics. That's where all energy states are allowed. And what classical mechanics says is that we can achieve any energy possible. Whatever it is, if there's 2 energies, we can find the one in the middle. Or we can find a higher one or a lower one, whatever. There's unlimited energy possibilities. So there's a continuum, if you would say, or you can plot out all the energies on a graph, and you can generate any energy you want. That's what classical mechanics says. There's continuous energies, and this really applies to macroscopic scales, things you can see. In contrast, modern science says, on the microscopic scale at least, subatomic particles, this would be physics 9B or maybe chemistry 2C, depending on your instructor, that not all energies are possible, only certain ones are allowable. So you can get to certain energies, like let's say you get to 100 joules, but maybe you cannot achieve 101 joules. That would be impossible, for example. That was where there's discontinuous energy, or not every energy is possible. Okay? This is modern science saying that there's discrete or discontinuous energy states. And this is what the genesis of quantum mechanics or modern science. And this is where things get weird because of that mere concept of continuous versus discontinuous. All right, let's try this example here. Here's a radio station, 107.9, Sacramento radio station. We want to know the wavelength. Okay, well, when you see FM, that stands for frequency modulated, or megahertz. So there's two ways to regulate the radio, through regulating the frequency or modulating the frequency, or AM, the amplitude. So mega means 10 to the 6, so this is 107.9 times 10 to the 6th hertz, or which is 1 over seconds, and that's nu. We want to find wavelength, which is C, which would be C over nu from our formula earlier. C is 2.9979 times 10 to the 8th. Remember, that's a constant. Wavelength, frequency I mean, is 107.9 times 10 to the 6th, 1 over seconds for this radio station. That turns out to be 2.778 meters. And if you think about it, that's why, I know current cars don't really have this, because it's built into the frame of the car. But if you have an older car, the antenna would be sticking out of the car, and it's about 1 meter long or so, and say this long. And that's why it has to be that long. It has to fit the amplitude. This is the frequency, but you get an idea of what the amplitude might be, because if it's the right length, then it's able to catch that wave or be absorbed by the wave. So because these waves are larger, you need larger antennas to absorb them. If you were talking about smaller waves, then you need smaller little antennas to be able to absorb them. Things now like cars, even your cell phones, the antennas are built into the frame of the structure, and so you don't see them. Okay, so that's it with that calculation. Let's continue to where we were, right there. And so what's the deal on this? In sections 2 through, I don't know, about 5, we're going to go through 5 different concepts that kind of illustrate why quantum mechanics exists. Okay? So there's going to be 5 different concepts in the next several sections that I'm going to go through. And the textbook goes through, so I just want you to be aware of those. Be on the lookout for them. They're listed on the top of page 58 of the reader. The first one you're going to see is atomic line spectrum. Again, these all illustrate this concept. That's what the first section is for, just kind of illustrating what the heck's going on. Okay, the first is atomic line spectra, and let me show you a picture. Here's what happened. People took different lamps that are filled with a particular compound or element, in this case hydrogen H2. And they turned on the lamp, and then like the prism kind of concept, they passed it through a slit to focus the light, and they passed it through a prism. And what we would think classically is that there is all possible lights are in all light. Okay? So we're going to see, again, a rainbow. That's what classically we would think, because all energies are possible, all wavelengths are possible, that sort of thing. However, when they did this, they got only, showing in this picture, 3 different colors. Okay? They got the red, the blue, green, and the violet at particular wavelengths. And this does not fit with classical mechanics. This fits with quantum mechanics because there's discrete particular energies, or lights in this case, 3 here, that show up. And so this points us towards quantum mechanics or modern science where there's discrete energies. Okay? And that's the concept behind this. Particular ones would show up here. We're going to learn how to calculate these energies or wavelengths in a little bit. But just let me show you a couple different examples. Depending on what lamp you pick, this is helium. And I'll dim the lights for a little bit so we get in the right mood. Okay? They're different. It gets different wavelengths. So it's not even the same as the other one. It's particular to the atom, in this case, or the molecule. So every molecule will have a different spectrum. Let me show you a whole kind of set of them here. There's mercury, helium, lithium. All of these have its own fingerprint of an atomic spectra, and they're all different. And so someone who studies this area can actually look at the atomic spectra and tell you what the molecule or atom is. They're that unique. And they're all different, and this, you know, for classical mechanics, it's like boom, blows your brains out. Amazing. Because this is not what was expected. This, again, is what's explained through quantum mechanics. There's discrete, particular energies. Okay. Now, what you're going to see in the textbook at this point is the following formula called the Balmer equation, where you can actually calculate these things. V, or frequency, mu I guess I should say, is 3.2881 times 10 to the 15th units of 1 over seconds times 1 over 2 squared minus 1 over n squared. Okay, and so, what's n, by the way? And the last chapter was moles. In this chapter, it's a mystery. They don't want to tell you. It kind of, the book kind of, and I guess I just followed them, is like, it's going to be a surprise what n is. We're not going to tell you. And basically you're going to find out at the end of the chapter what n is. They're going to reveal it slowly. It's like some sort of murder mystery. Okay? So anyways, n, the first piece of information you get to learn about n, it's a whole number, a counting number, like 1, 2, 3, 4. If you put in counting numbers into this, starting at 3, what's kind of cool is you can calculate ultimately these wavelengths using the Balmer equation. I'm not really going to use the Balmer equation in our class. There's a better equation, in my opinion, coming up that I'll teach you about, and when we get to that one, we'll do some math and you'll see how to do these calculations. This one is a little limiting, so I'm going to end up not using it. Okay? Alright, but there is a way to do those calculations and find out what the atomic line spectra wavelengths would be. Okay, so that's the first one, atomic line spectra. Here's the second of 5 concepts. It's called black body radiation. Okay. A black body, okay, not using the radiation term, is a term in science where we say that that kind of object absorbs all light and doesn't reflect any of that light. So where all light is absorbed is called black body, or a black body. Now black body radiation, what that means is if it does reflect light, we call that black body radiation, or if it does reflect any energy. So any, of all the absorbed energy, anything that's reflected is called black body radiation. I don't know if you've seen any of those kind of advanced thermometers where they just take it and they point it at something and it reads the temperature. That works via this concept, where reflected energy is read by a little thermometer device, and as it's read, it converts it into a temperature. Okay? That's from black body radiation. So this is reflected energy. Okay. Why is this interesting? Oh, and there's all kinds of different things can be modeled as a black body. The ideal black body, if it exists, would be a black hole. By the way, a black hole is something that absorbs everything into it and nothing can escape. What's on the, if you go into a black hole, what happens? Yeah, you go into the alternate universe and you come out a squirrel. You come out a white hole, which reflects everything, supposedly. But that sounds a little disgusting when you say it out loud. Okay. Anyways, there's a lot of things that have black body radiation. Okay. Humans give off radiation as well. Okay. Now what's the big deal on this? Let me show you this graph here. I'll show you this one right here on the top. Okay. Here's what we thought classically. Okay. As you decrease wavelength, going this way on the x-axis, you're actually increasing energy, or you can increase intensity of the light. Okay? So classically, what we thought is what's represented by this black line right here. And let me dim the lights a little bit so it's easier to see, or maybe I'll dim them all the way, I'm not care. So that first one, I'll turn the lights on in a second. Don't worry if you're scared. Grab onto your neighbor. As we decreased wavelength, we expected classically to be able to get to higher and higher radiation values from black body radiation. Okay? So we expected higher and higher radiation or energy intensity values. So we expect this to go up and up and up to infinity and beyond. Here's what actually happened though. We realized, depending on the temperature and what the radiation was, you actually reach a maximum. And then it goes back down. So you cannot go to the highest possible energy. There's a limit on the energy, or we might say the energy is discontinuous. It does not continuously, the intensity does not continuously go up and up to infinity. It has a maximum. And so again, we don't receive all possible energies. You can't go all the way up on the y-axis. There's a limit. And so there's certain allowable energies. And black body radiation is now our second example to demonstrate that. Okay? We're not going to do any calculations with this. This is just purely conceptual, as far as we're concerned. Maybe if we get to later classes, you'll see some, we'll do some calculations with it. But the textbook does introduce a formula in this part, which I want to introduce too. We've already seen this formula, C equals lambda d. Saw that one. Here's our next, we saw bomber, but we're not going to use that equation. Here's the next equation we will use. Energy equals H nu. Nu is still frequency. That's frequency. E is energy. Again, what's the units of energy? Joules, just like the previous chapter. And then we have H here. H is called Planck's constant. That's right. Planck's constant. It's a number I'll give to you. I'll also give you the speed of light on the exam. But it's 6.626 times 10 to the minus 34, and the units are joules seconds. That is joules times seconds. Okay? So if we take the example we had before, where we were doing that 107.9 radio station, which they should pay me money for saying their name so many times. You can calculate the energy of that radio station using this formula, just as an example. You would say, oh, that's Planck's constant, 6.626 times 10 to the minus 34 joule seconds, times its frequency, which we remember before, 107.9 FM or megahertz. It's 107.9 times 10 to the 6th hertz, which is 1 over second. And in this case, when they're broadcasting at this energy, 7.19 times 10 to the minus 26 joules. So when that radio station is broadcasting, it happens to be at that particular energy. So now if you know frequency, you can find energy. Sometimes we'll combine those two formulas. So instead of writing E equals H nu, we'll write equals HC over lambda. Okay? This comes up with black body radiation and Planck and all these guys who are doing these derivations. We're not going to do any derivation related to it. I'm just showing you the formula. Okay, so we finished the two concepts, atomic line spectra, and we finished the black body radiation. Now, concept number 3, this is page 59 of the reader and of the textbook. This is page 252. Concept number 3 is called the photoelectric effect. Anybody know who is the main scientist behind this? Einstein, yeah, he's better known for relativity, but this is what actually got him, for certain political reasons, the Nobel Prize. Okay, so what is the photoelectric effect? It's the following. Okay, so it's our third concept here. If you take a metal, and we're using a metal in particular because metals have a fluidity with electrons and kind of do interesting things with their electrons. And let's say we put in energy here. Okay, we put in some energy, shine energy at the metal. First, what would we expect classically? Classically, what you expect, because electrons are so fluid within the metal, and that's why they're great conductors of electricity, because of the electron movement, as you put in energy, a little bit of energy gets a little bit of electrons to bounce off of the metal. More energy, more electrons come off, etc. So the higher the energy, the more electrons you can get off. That's what we expected classically. However, that's not what happens. You start putting in energy, nothing's going to happen at first, until you reach what Einstein called the threshold energy. That is a high enough energy at which you can remove electrons. Okay? But it has to be a certain threshold energy. Any energy won't do it. You need to reach a certain threshold for this to happen, and this fits under the quantum mechanics idea. There's discrete energies. Not everything is allowable, not everything works. When you reach the right energy, then things start to happen. Okay, that's the discontinuous nature of quantum mechanics. All right, that's concept 3. No math with that one. Where most of this is all going to be conceptual. Now we're going into section 4 right now. Before we, and that's not concept 4, this is section 4. I'll do this. Section 4, atom. We're going to take a little interlude to say a little bit more about one of the concepts we just talked about. And to introduce the topic, I need to say a little bit about the Bohr atom. Okay. Let's see if I have a picture of one. Yeah, I do right here. Okay. Bohr came up with 3 things that resulted in his model of the atom, which is this. He said, electrons orbit the nucleus, kind of like planets orbit the sun. Okay, so electrons orbit, so you see all these orbits, 3 in this case. The orbits are fixed. That is, you have to stay on your orbit. Okay? So the orbits are fixed, that's the second thing he said. And they're fixed at a particular energy. So the lowest energy is orbit 1. As you go farther out, it's a higher energy for orbit 2, and the highest energy for orbit 3, and so on. Okay? The last thing he said, or the third thing he said, electrons can change orbits if they want to. The orbit won't change, but the electron can jump from one orbit to another orbit as designated by these arrows here. Okay? So they can change orbits. And this is the concept behind orbit changing that you should be familiar with. If you put in energy, an electron will jump up in orbit to a higher orbit. Okay? If electron then wants to go back down a lower orbit, it has to release energy, and that energy is released in the form of light. Okay, that's the main concept you should be familiar with. Energy, when electrons drop down orbits, are released in the form of light. So you're seeing light coming out of these fluorescent lights in the ceiling. That's because electrons are falling down energy levels. When they're falling down energy levels, light's moving off. Okay? So, and it doesn't matter what the light is. So, you put in energy, electron goes up in orbit. When the electron falls, energy is given off in the form of light, or more specifically, electromagnetic radiation. Okay, hey, check it out. Here's N again. Now we know a little bit more about the mystery N. Again, it's a counting number, 1, 2, 3. It goes with the orbits. And so you know two things. It's a whole number, a counting number, and it has to do something with the orbits. Okay? It's not the N from the previous chapter that has to do with moles. Alright, so we know a little bit more now about it. Just to give you a couple more examples of light. If you've heard of the aurora borealis and all the colors of the aurora borealis. This, again, when electrons drop energy levels, these kind of lights are given off. If you see more of the greenish colors, that's electrons into oxygen. If you see more of the red and the blue colors, depending on what's going on, that's from the nitrogen electrons. So kind of depending on where it's coming from, that's the color and sort of thing that you see. So any sort of light, that's where it's coming from. If you think about light bulbs, these are fluorescent light bulbs. Say I have more of the office, like stale feel, the blue color. That's because those electrons are coming off towards the blue side of the visible spectrum. If you go home and you have an incandescent bulb, and it has that warmer color, that's because those electrons are coming off near the red side of the visible spectrum, so it has a little warm hue. Alright, now, I need to teach you an equation. This equation doesn't really have a name, but I call it the Rydberg equation because I want to call it something. Rydberg. Doesn't really have a name, this is just what I'm going to refer to. The change in energy of those electrons jumping up and down energy levels is the following. It's the Rydberg constant, RH, 1 over n, here's that n, initial squared, minus 1 over n final squared. What are the n's again? N initial, okay, n initial, and n final. Orbit initial, orbit final. What's this? This is a constant. Okay, and by the way, we're on page 61 of the reader. This is a constant. It's called the Rydberg constant, and it's 2.179 times 10 to the minus 18 joules. Okay, it's a constant, has joules as a unit. Okay, now, let me flip back a little bit. Let me show you something. We're going to go back to concept 1, atomic line spectrum. We'll use this equation a little bit so you can see how it works. Okay, here's the Bohr model of the atom. Okay, just drawn out with a number of different orbits. And this is how it connects to the hydrogen atom. When an electron drops, there's the atomic line spectra on the top of the hydrogen atom. When an electron drops from the third level to the second level, that's where the red color comes from. When it drops from the fourth to the second, there's the blue-green. When it drops from the fifth down to the second, that's the violet. And that's how that's why those different colors come about on different atoms. And because different atoms have orbits at different energies, they'll give off different light. Okay? So because, again, the orbits will be at different energies for different atoms or molecules, different light will be given off based on the electron drop from higher to lower energy levels, and that'll cause your characteristic atomic line spectra for a particular atom or compound. Okay? Does that kind of make sense, the combination of those concepts? That's why we're doing the Bohr atom now, so you can see how the two concepts sort of go together. And I know you're wondering, wow, there hasn't been much math recently. Can we do some math, please? Let me just show you how the math would look, and we're going to do an example in the next lecture. But basically, you can do this calculation where you say, oh, if the electron drops from 4 to 2, that's the blue-green line. All you do is use the Rydberg equation and put 4 and 2 in here, from the initial to the final. Okay? And you can find the amount of energy given off just by doing a simple calculation. But we're going to do a calculation like this at the next class, so you can write this down if you want, but you don't need to. Alright, let me put this away. So that was redoing, kind of a revisit of concept 1. What's really interesting about the Bohr model of the atom? Is the Bohr model of the atom how we see the atom right now? Not exactly. It's a helpful model that we're going to use for calculations. It gives us some valid numbers, but that model, the model does have some flaws. But what's really interesting about it, if electrons did not stay on their orbit and they could go wherever they want, it would be the total breakdown of all chemistry. Because the fact that electrons can stay on their orbit and have a fixed path allows us to do chemistry because we know where the electrons are, and it's not just a mush pot of electrons flying everywhere. So the fact that they stay in one place makes it very unique. Oh, let me toss out something else interesting. Remember, electrons can only exist on an orbit. So how does the electron get from one place to the other place? Quantum mechanically, we say it happens in 0 time, instantaneously, and it's not allowed to pass through this space, otherwise energy would exist in this space. Somehow it goes from here to here without going through the middle, however that happens. You can figure that out. Okay? That's the sort of stuff quantum mechanics tells us. Alright. Section 5. 2 more ideas. So this is going to be idea 4 and 5, or concept 4 and 5. Concept number 4. Okay? It's called the wave-particle duality. Wave-particle duality. This will have a little bit of math associated with it, and this is page 61, 62 of the reader. And in the textbook, we're getting to page 262. Okay, what does this say? A light can act both as a wave, if it wants to, and a particle if it wants to. So light can be a photon and act as a particle, or it can act as a wave, whatever context it's in, it can decide what it's doing. It's a weird concept, so that means quantum mechanically everything, a baseball, you have a wave function and have a wave-like properties, according to this concept. Because you're so fat, according to quantum mechanics, you're not a subatomic particle, we don't see that wave function play out visibly. Okay? Otherwise, it's not like we walk right to left in the wave function. And it's described by this equation. In this equation, does anybody know what P stands for? It's equal to mu. Momentum. Momentum was what variable in the previous chapter? Capital I. Yeah, now we're using lowercase p. It's momentum. It's equal to mass times velocity, just like the previous chapter. What's h? Yeah, we just saw it's Planck's constant. What's u? We saw in the last chapter. Velocity. And what's m? We saw it before. Just mass. Okay? So this is really interesting because we have something that has a mass here in this part of the equation and something that has a wavelength here. So it has both a mass and a wavelength. Okay? This we call the de Broglie equation. De Broglie equation. It's basically a plug and chug equation where if you have a mass, you can find its wavelength. So we'll do this for a baseball. Okay, there's a baseball. Let's say the mass of a baseball is 0.5 kilogram. And let's say somebody throws it 100 miles per hour, which would be about 44 meters per second. What we want to do is find the wavelength of that fastball thrown at about 100 miles per hour. So you just use the equation, lambda equals h over mu. H is Planck's constant, 6.626 times 10 to the minus 34 joule seconds. M, in this case, is 0.5 kilogram. And the velocity in this case is 44 meters per second. It's basically a plug and chug sort of calculation. You get the wavelength to be 3 times 10 to the minus 35 meters. That means the wavelength is all pretty much negligible. You can't see it, though it would have one. Okay? So you're not going to see the ball wiggling from side to side as it goes towards the batter. Okay, so this is the wave-particle duality, or specifically the de Broglie equation. Why does this kind of mess with quantum mechanics? Because here it says everything that's particulate or a particle can have a wave. And so there's this kind of dual personality where something can be a particle sometimes and a wave at other times. Last concept of the 5. Concept number 5. Last of the 5, also in this section, is called the uncertainty principle. Uncertainty principle. Sometimes you'll see the word Heisenberg tossed in there. So Heisenberg principle, Heisenberg uncertainty principle, any combination thereof. Here's the concept. You can either, it says you can either know the position of something or the velocity of something accurately, but you cannot know both accurately. Classically, we would think you can know both accurately. Classically, in the previous example, we would say things can't be both a wave and a particle. So this says, again, you cannot know both the position and the momentum or velocity precisely and simultaneously. So you can't know both of them. This had a big fight kind of ensued between Einstein and Niels Bohr at this time over this principle. Einstein said, hey, we can't know things accurately because that's insufficiency due to our ability to measure. So we're not able to measure well, and so there's an uncertainty. It's our fault. Niels Bohr, on the other side, said, no, this is a characteristic of the system. The system says it is by nature uncertain. There's by nature probabilities associated with things and not certainty. So they have this fight. It turned out in this case, Niels Bohr won, and it turns out that the system is uncertain. That is where somebody says, hey, you can know everything for certain. That's not true anymore according to modern science. The equation that goes along with this looks really weird. It looks like this. You know all these variables pretty much. H is Planck's constant, pi is pi, 3.14. 4 is the number 4. This is a greater than or equals to sign. What's P? Momentum. And the only one you probably might not be familiar with this is length or distance. Distance or position, that sort of thing. A length, a distance, measurement. So this is the Heisenberg uncertainty principle equation. We're going to use a different form of this. Oh, the deltas. I didn't mention the deltas. The deltas that represent uncertainty. So how we're going to use this is the following. when you see me do calculations in class, I'm just going to drop the delta. For momentum, I'm just going to say mass times velocity. And to represent the deltas, I'm going to include a percentage here, which will be our percent uncertainty, or a synonym thereof. We're going to use an equal sign, h over 4 pi. And this is the way I'm going to use the equation, though on the test, I'm going to give you the actual equation. Okay? Well, what I'm going to do is next time, I'll show you how to use this equation. Okay?